Hello, explorers, and welcome to Reach the World's Explorer program. For more than 25 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens through virtual exchange. My name is Tim, and today we're taking the next step on our journey through the world of supercomputers and research software engineering. We've already visited the San Diego Supercomputer Center to see what a supercomputer actually is and how it works. And today you'll meet Ian Cosden, the director of the Research Software Engineering Group at Princeton University. He's going to tell us how he helps scientists harness that extraordinary computing power by engineering cutting-edge research software. If you haven't already read Ian's Virtual Exchange article, there's a direct link in the chat area. This will take you to the Virtual Exchange Journey homepage where this and all future articles for Reach the World's Supercomputing and the Future of AI Virtual Exchange will be published. We've got several classes joining us live today. Hello, mostly via YouTube. A very special welcome to Ms. Copeland and students at Green Street Friends, and of course Ms. Mesk and her students at PS1. Hello, waiting backstage. It is great to have you all here with us. After we hear from Ian, I'm going to turn to you for all of your research software engineering questions. So please be thinking about what you'd like to ask Ian and drop them in the chat bar at any time if you'd like. We'll get to as many questions as we can today. Okay, housekeeping complete. I'm very excited to welcome to the screen the director of the Research Software Engineering Group at Princeton University, Mr. Ian Cosden. Let's bring him on stage. Hi, Ian.
Hi, Tim. Nice to see you. Morning, everyone.
It is very nice to see you too. Good morning. We are so excited to meet you and have your voice join this journey, this learning journey we've been on, because as I mentioned in the introduction, we've been to the San Diego Supercomputing Center. We've now seen what a supercomputer looks like physically, but I feel like you're going to tell us how this all comes together through the work that you do. So without any delay, I'm going to turn it over to you to introduce yourself and what it is you do.
Great. Yeah, thanks, Tim. Morning, everyone. So my name's Ian Cosden, and as Tim said, I lead a team of research software engineers at Princeton University. My background, when I was in 5th grade, I did a project on the internal combustion engine, and from that point forward, I thought that cars were the coolest thing in the world, and I wanted to design cars. And so who designed cars? Mechanical engineers. So I went and got a degree in mechanical engineering. I worked there a little bit. Turns out I didn't really want to design cars anymore. I did a PhD in mechanical engineering where I looked at heat transfer on really tiny scales. We're talking smaller than a human hair, which was interesting, but it turns out what really got me excited was writing the code. So using programming to solve the science and engineering problems that helped give that physical insight of how boiling worked at the nanoscale, which is, again, super microscopic, and we use computer simulations to do that. So that started my discovery of that I really loved writing scientific software and research software engineering more broadly. This is it's kind of a new field, but it's something that has exploded over time, including here at Princeton, where we work with researchers from humanities, so people looking at ancient Greek texts through the microscopic of subatomic particles up through astrophysics and stars that explode, and as well as modeling biological systems and the human genome.
All right, amazing. Before we dive into some specific examples of your work, you mentioned in your article that there is a difference between the people who are, creating apps for your phone, your smartphone, or, doing some of the other coding we might all see and use on a more regular basis in our personal lives. I want to dive into your projects, and we have some great pictures of some of the things you're working on. But can you start by sort of telling us the difference between those two?
Yeah, sure. So I think there's a couple. First of all, a lot of times we have phones and Chromebooks and all kinds of apps that we interact with on a regular basis, but they're not solving essentially equations. So doing really heavy, challenging. Maybe I can give you an example. If you take 1 plus 1, that equals 2, right? And so that's a single addition operation. Some of the things that we have to do to solve science problems involve millions, billions, trillions, times and times again of doing these additions, multiplications, subtractions, um, over and over again. And that's a lot different than displaying videos, creating interfaces that we use the mouse and click on and interact with. A lot of times this is just numbers and text, and crunching scientific equations in a way that we're trying to harness the powers of supercomputers, which I can talk a little bit more about later, in a way that can use all that horsepower, all that really powerful computing to solve problems in science that we've never solved before.
Is it safe to say on a basic level, though, that if you are learning the basics of coding in elementary school or whatever class you're in right now, that you may be interested in a career in research software engineering?
Yes, a lot of the same basic principles start. One of the things that we like to say is it utilizes all the skills you'll learn as a programmer and developer, but we get to apply them to scientific discovery.
Excellent. What a great segue, because we are here to explore. We're here to explore the world through supercomputing and research software engineering. So let's see a little bit about how you do that.
Yeah, sure. So this is me talking at a conference. Um, my group at Princeton does is that we partner with scientists. So this might be a biologist, it might be a chemist, it might be a sociologist who's trying to understand how families work at home, and they have either the need to simulate something, so that is create a model, or they might have a lot of data. They might have a lot of information. Maybe it's things they pulled off of the internet that they need to crunch and they need to figure out and get some insights from that. So what my team does is we connect with them. We try to understand what their problems are, what they're trying to solve, and figure out the best way to do that by harnessing some of these supercomputing uh, resources.
Great. We're going to skip this
Come back.
interesting car slide and come back to it. Don't worry, we'll come back to it, kids. But proceed.
Yeah, so this is a sample of some of the research work that I used to do that I needed to use supercomputers for to solve, which is if you look down at the bottom left, the A, B, C, D, E, F is actually, those are particles that are forming to create a bubble out of a hot liquid. And so we would run simulations and computer models that ran on supercomputers. We couldn't do it without supercomputers, that allowed us to understand what was happening at these very early stages when a bubble starts to form. So you may have seen this before. This is me. I'm not a graphic artist, but this is my example of what a supercomputer is. And it's important because as we programmers who are going to use this, we have to understand how it all goes together so that we can then write our code in order to utilize it. So glossing over some of the details, the way I like to think of a supercomputer is it's just a lot of pretty regular computers all connected together by these red lines. And if it wasn't for the red lines, it would just be, maybe a laptop sitting on the desk all over the classroom, piled high. But if they're not connected, they don't work together. And that's what makes a supercomputer really special, is that they can work together. And that's what we need to do as programmers. This is a picture. I think you've gotten a tour one, but if you haven't, this is kind of what a supercomputer might look like. It's just racks and racks of of essentially standalone computers. Each one could be by themselves, in these special rooms that keep them cold because they can get really hot. Let me go to the next one and show you what the back looks like. Remember I said they were all connected? Yeah, it gets messy back there. They are all connected. Each one of these green lights is its own computer, and this is one rack of. You remember there were many, many, many of them, all tied together in a way that lets us utilize them at the same time. Okay, it does get complicated, and this is why I have a job and why my group exists, is because this is code, and maybe if you're starting to write code, you can start to see some commonalities here. Doesn't matter exactly what it is, but what's interesting is that this is literally just sending a message between two connected computers. It gets really complicated when I want to send one number from one to another. We have to write a whole lot of glue around passing things back and forth. We actually call it message passing. And that's how we get them to work together. The cables connect them, and then we, the programmers, have to send what each one needs to know back and forth to each other. Maybe we can go to the next one. Again, I don't expect anyone to know this other than the fact that equations can get really complicated. They can start simple and then get complicated. And that's what we have to write in our code to solve these, because a lot of times the problems we're doing actually all boil down to math. And we're solving math on supercomputers, and it's a lot of math. So maybe we can go back to the car picture at this
Let's
point,
do it. Yep.
and I can tell you a little bit about this. So this I love this picture because it describes, it's an analogy about how we as programmers utilize supercomputers. Here's a car. I'm not a racing fan, but I do know that they're trying to get this car back on the road as fast as humanly possible. They need to change the tires, they need to fill it up with gas, they need to service it as quickly as possible, because if they don't, they're going to lose the race. So if we look at this closely, we see there's a few things happening all at the same time. First, we've got 4 tires being changed. Each one is being changed by a team, right? It looks like somebody's maybe holding the new tire, somebody's unscrewing the bolts that keep it attached to the car. There's somebody else who's propping up the car so that they can do that. And they're all working together very effectively, efficiently at the same time. This could happen if one person did it, but would be a whole lot slower. So what we can think about is we do the same things with the problem we're trying to solve. The problem here is, how do we get this car back on the road with new tires, gas, clean windshield, etc., as fast as possible? And we split that into smaller tasks and we give it to the team members. So there's lots of folks here. Everybody wearing a helmet is in some way contributing to this problem of trying to get it as fast as we can. So the analogy here to how we do programming is, we might say, computer numbers 1 and 2, you work on the back left tire. Computers 3 and 4, you work on the back right tire. Computers 5 and 6, you work on filling the car with gas. Computers 7 and 8, you work on the front left tire. And I think you can kind of see where this goes. By me saying that out loud, that's what we, the programmers, do. We have to write this down, and we have to say, work on this piece here, here, and here, with the goal being that everybody starts at the same time, everybody ends at the same time. Because if it's just one, say the person trying to put the front left tire on has a problem, everybody else is standing around waiting for that one task to finish, and the car's not going to get there. So this is a nice sort of way to think about how we have to approach some of the challenges we get, and it's different for every problem. And that's what we do, just in code.
That is just a wonderful metaphor or example of showing how you do it. And I want to take a moment to pause here because we have some students who can have to leave a little bit early in the next 15 minutes. And I want to give them a chance to ask you their questions. I'm sure I have some questions based on that, and I want to give them the chance to ask their questions. So we're going to welcome our friends at PS1 in Brooklyn. Hello, friends at PS1.
Hi.
Great to see you. Did anyone just hear what Ian had to say and has a question they want to ask him about any aspect of that? The floor is yours.
All right. I'm going to start over here with Yadiel. How long does it take for the gas to fill for the car?
How long does it take for the gas to put in the car? That's a good question. I would guess seconds, because again, they're trying to go really fast. So did you see how big that pipe was? It was pretty big. It's bigger than the one you have at your gas station. And the reason they do that is so they can get it in the car really fast.
All right, I'm gonna go over here to Layla. Go ahead.
I have a question. How for the equations that you showed us, how can you like memorize all of that? Because it's a lot of numbers, symbols, letters. Yeah, a lot of random stuff. How can you remember all of that? Because it's really hard, and complex.
So I think I heard, how do you remember all the really hard and complex numbers and symbols and math? That's a great question. And honestly, that's why we use computers to solve these, because it's really hard to do it with a pencil and paper. So what we do is we slowly put them into computer programs, and we keep track of them. We do it very carefully, and we make sure that we get it all right as we move along. And then if you've had some experience programming, you know that once you write it, it's still there and it's there forever. And then we can keep building on top of it. So what starts off as a pretty simple equation, we can get more and more complicated over time to solve things for the first time. So great question, and that's why we use computers.
Athena.
Are you yourself really bad at math?
Sorry, I couldn't hear it.
Are
Can you say
you
what?
really bad at math?
Am I really good at math? Is that the question? So yes. So I will say I always enjoyed math. Math was something I had to take a lot. I joke that I went to many grades of college after, and math underpins a lot of what we do. But there's all different kinds of really complex math or easy math that we just need to do fast, and sometimes that's challenging as well. So math is very helpful in pretty much everything we do.
All right. All right, I'm gonna go over to Moise now. Moise, go ahead.
When okay, when you first started engineering, were you nervous or were you like a little nervous to start engineering?
Yeah, sure. So every year at school, and then high school, and then college, and every time you take on something new, it's a little nervous because it's new and it's complicated, and you haven't seen this before. And to the earlier question, sometimes the math starts to look a little scary. But like anything else in life, I think if you take it one step at a time, and there's a natural progression, you look back and think, oh, I really did do that. That wasn't so bad, even though it feels a little nervous at first. And when you start in engineering, everybody says, "Ooh, that's really hard," and it is, but you can do it.
All right. Other questions? Other questions? Evelyn, did you have a question?
What do you like to do in your free time?
What do I like to do in my free time? That's a good question. So I have 3 kids. I have a ninth grader, a fifth grader, and a second grader. And I like to, they are all in various different sports activities. So I like to go see their soccer games, lacrosse games, dance recitals, etc. And like playing outside with them in their various sporting events.
We have a couple more hands. Joaquin,
Are you good at science?
are you good at science?
Thanks. So I will say that I have a background in science, but I work with scientists who are scientific experts. And so they are the world leaders in their field. And so I know a little bit about what they do. But that's not what I have to do. I know a little bit about a lot of things, and that helps me contribute through writing code and software engineering.
Okay. Do we have time for 2 more questions?
Yes, we do. Please go ahead.
All right, Gabrielle.
So, if a supercomputer goes as fast as the speed of sound, so doesn't this mean like normal computers just go at normal speed?
Okay,
So he's asking, like, if you compare a supercomputer with a normal computer, how would you compare the speeds?
that's such a good question. So in fact, have looked up. So a normal computer, the way we measure computers is we say how many times can they do a single addition, right? So how many times can they do 412 plus 519? And a normal computer can do around 2.6 trillion of these a second, right? A lot. That's a normal computer. I can't lift it up, but my normal laptop can do that. The best supercomputer in the world right now can do about 1,000,000 times that. Okay, so imagine 1,000,000 computers. If you've got one in the classroom, just look at it. Now imagine 1,000,000 of them together. That's how much more it can do. So suddenly, if it were to take me 10 years to do a certain simulation, whatever it is, we're talking seconds that a supercomputer can do it. So instead of waiting 10 years for a result, you can get it in a second. And that's pretty amazing. So yeah, supercomputers are really, really powerful. And they cost a lot of money and they're really, really hot.
Layla, have you ever visited any schools or like buildings and and gave like a speech? And would you ever visit our school?
Thank you. I appreciate that. I have gone to schools. I've actually talked to a number of computer science clubs. So something that comes along in high school or some options to where if you get into coding and you like this, that you can join a club and you can start to do it more. And I've certainly talked to students at that level, again, about what we do as research software engineers. So I would be happy to visit students. I think it's great to share with what we have, and I'm excited that you're here today.
All right, I have one more hand. Is that okay, Tim?
Yes, please.
What is 1 divided by 0? What?
He's quizzing you.
What is 1 divided by 0? I think you're trying to trick me. I think that's undefined, and I'll tell you what, sometimes when we try to write that in computers, we get an error message. And that sometimes is a hard error message to find out where we messed up.
All right. PS1, thank you so much for the great questions. It's fabulous to have you join us live today. I'm going to move you backstage. Have a great rest of your day. We have, Ian, a bunch of questions from Miss Copeland's class as well, and I want to touch on a couple of them because they address some of the early things you talked about in your presentation. And I'll bring up the first one. Julian wants to know what the complex math equations you referenced are for. What are these equations trying to solve?
Sure. So that was an example of a definite integral, which is something that you learn in calculus. And if you want to think of, can you imagine a graph, a line, and we want to figure out how much area is underneath it. This stuff comes up all the time in various different sciences. It's kind of a math idea, and it comes up in problems. But what the point of showing that is that that's where we start. What we have to do is we have to manipulate it and change it in a way that allows us to split it over different computers. So we can solve that one problem, that what started on the left, into lots of little chunks, kind of like the analogy of the race car. We split it into little chunks and have every computer work on its chunk, and then put it all back together at the end. So it's it's the idea that what starts off as something kind of basic and simple, we have to make more and more complicated in order to harness the supercomputer's power.
All right, fabulous. Great question, Julian. Thank you so much. There's some interest in, our day-to-day involves computers with screens. You don't know what the computer is doing if you don't have a screen to see what it's doing. And all the supercomputers we've seen so far, as referenced in Asa's question here, don't seem to have screens. How do you know what they're doing?
Great question. Good point. Very observational. So what we do with supercomputers is we use our own computer and we connect to it remotely. So we almost call it up and we create a connection. and it allows us to interact with it. So and then there's a screen, but most of the time we don't use we don't have point and click, we don't use a mouse, we have a single line terminal. We call it a command line, and we use text instructions to communicate with the supercomputer. So it actually looks very simple and very boring, and we might just say, run this program, enter. And we've built up all the program, we've set it all up, and then it goes, it spreads off, and it spreads out to all the different machines, and then it logs things. So it will write them the files, and then we have to come back, collect those, and take a look at what happened. So sometimes a lot of our job is spent trying to figure out what exactly happened across tens, hundreds, thousands of different computers all at the same time working on the same problem. Sometimes stuff goes wrong on computer number 789. We've got to figure that out, and we have to use text logs to do that.
All right, fabulous. And I want to add one more question here before we return to how you're using the software that you're engineering to explore the world. Everybody here is an explorer. We've connected with, people who are out in wild places, doing sort of typical exploring of wild places. And software engineering is just as much exploring the questions you're exploring. So we want to get to that, but I have one more question here, and it's from Luke in Miss Copeland's class. He wants to know if you actually had all the computers working on the same part, like the back left tire, great reference to our race car analogy, would it go much faster?
Luke, I got to tell you, this is a really great question because it's very insightful on the answer is usually no. And this is something that I actually, when I teach how to do parallel programming on supercomputers to college students, they sometimes get wrong. So I think it's really great they ask this question. And so let's use that same idea of what would happen if you took all the people in the world and had them try to change the back left tire. They'd be bumping into each other, and they'd be making a mess, and somebody would fall over, and the people in the back would be pushing to try to get up, and it would take way longer. And it's actually the same thing. What happens is you try to split the problem into so many tiny little pieces that it takes longer to say what those tiny little pieces are, work on them, bring the information back, collect it all together than it would have if it was just a few. Now, it depends on the specific problem. It depends on a lot of things, but there's almost always a point where it doesn't go faster. It actually starts to go slower. Again, it just depends.
All
So
right.
Great question.
Fabulous question, Luke. And Braylon, Penn, and Ruby, I'm going to hold on to your questions for the time being because Ian's got a couple more things he wants to show us about his work that I think you're going to be really interested in. And then we'll return to more questions, and we'll see if you have more questions about this. I expect you will. So over to you, Ian.
All right, so I've got lots of examples. So one of the really neat things about supercomputers and then writing code to use those supercomputers in research is there are tons of different applications in the research world that use this that wouldn't be possible. So I've grabbed a few pictures from projects that we're working on right now I'll go over real briefly. We can chat lots more about them if you're interested. So like, for instance, in the top left, these are experiments that take particles and crash them into each other, and then subatomic particles go flying. They need to track very fast from cameras that are watching these. Cameras is kind of a loose term. And then figure out what that path is. So we use supercomputers to piece together tracks of subatomic particles after these collisions. Or there's this blue picture that looks a little funny. That's a particle reconstruction. So we have a great example was the coronavirus, the actual virus structure, froze it. They took microscope images, and they got these really blurry, messy microscope images, and they need to figure out what the structure of this virus looked like, or lots of other particles. And so we can use supercomputers to take these blurry, messy images and reconstruct what the actual molecules look like And sometimes we use AI to do that. Sometimes we just need to use a lot of images and a lot of different image processing on supercomputers to do it. The one in the middle is essentially modeling earthquakes. So what happens if there's an earthquake? Can we run a computer simulation really fast right away so that we could warn others what might be happening later? Or we could understand that in certain situations what earthquakes might do. Perhaps we can better prepare in the event that earthquakes can happen. Now this is, as you can see, it's modeling the entire Earth, and a change in the Earth that takes a lot of supercomputing power to model everything on the Earth. The next one over is about looking at groundwater. So what happens if it doesn't rain in Colorado for 3 months? What would that mean for the rivers downstream? How would water policymakers, how would water companies plan and prepare? So we have simulations that can say, okay, what happens if that does? What's it going to look like, and how can we help people prepare for that to happen? The one in the middle is an example out of the social sciences and sociology, and we have voter registration information, and it's um, bigger than would fit on one computer, but we have all this information. We're trying to understand different populations and how they might vote and how they might react to certain things. So this isn't science so much as it is understanding politics and things like that in the extracting from really large amounts of data. Okay, on the bottom left, these are the black parts are hair follicles on a mouse, and they're trying to understand how they start to form uh, early on, and this has ramifications for things like cancer research. In the middle, there's these old ancient texts that we're trying to digitize. That means put them in computers in a way that researchers can then search through and try to understand what was happening in the 10th century Egypt, for example. Why were people writing stuff? I think in this particular case, this happens to be something along the lines of like a shopping list, but even that's interesting, and researchers can try to understand what were people doing back then, and how were they working if we can take the image on the right and turn it into something that computers can learn and understand and work with on the left. On the bottom right, we're looking at hydro wind power and clean energy sources, and how that would affect our energy grid in ways that um, can help us get away from fossil fuels. And so we can do simulations of what happens if it's really windy this day or not windy on the next day, and what that means for keeping constant electricity all the time. Then,
Wow, that is amazing. It sounds fun. It sounds like you get to work on a variety of different problems, seeking a variety of different questions using this really powerful tool. You're the person who sort of connects the problem to a possible solution through the software.
exactly right. Yep.
That is amazing. I'm going to leave that slide up just a little bit longer so that our students can take a look at it and think about whether they have any questions about any of that. Some of the questions that I've seen in the chat since you started talking about some of your current work have to do really with like wrapping our mind around the power of these are big. You've successfully described these problems as enormous problems with a lot of data, something my laptop couldn't handle, your laptop couldn't handle. So let's bring in a couple more questions about the computers themselves that are powering these things. Like how long, for any one of these questions, Braylon wants to know, how long would it take a supercomputer to give you an answer, to run a simulation about groundwater, for example?
Yeah, that's a good question. I'm gonna say right now, let's say on the order of many hours to a few days. Um, and of course, it depends exactly on a lot of different details. But what I think is pretty funny, I've been doing this for a while, is that number always stays about the same, Braylon. It's always a few hours to a few days. As things get more powerful, the problem just gets bigger. The questions we ask get bigger. So instead of if it was just the groundwater in Colorado, it might be what happens if there's a drought in Colorado, also one in Washington State and one in Florida all at the same time. Right now we couldn't do that. That would be too big a problem. But in 5-10 years, maybe we can.
Well, and I think it's probably worth asking as well, just from my perspective, when you hit go, run this great program that you've designed, does it always work exactly the way you intended to?
Almost never.
You just come
So
back in a day and you have your answer?
So yeah, yes and no. So when we're developing, so when we're trying to get this started, when we're taking those equations and we're turning them into software and we're writing the code and we're taking it one step at a time, there's always problems. We call them bugs, and the bugs are always there and we're always having to deal with it. We spend a lot of time making sure what we get is correct. Once we get it, one of the beauties of software and computers is that it will repeat that over and over again. So we can have some confidence that once we get it correct, we can click go, send it off. In fact, we can click go 300 times. It goes and sits and waits its turn, and it just churns off the first, the second, the third, all the way up to 300. We come back in a week and take a look at our science results, pass them on to the scientist, and they can then say, oh, we need to change this or we need to do this. And this is the scientific insight that we can get as a result of the simulation.
All right. Fabulous. Real quick, Penn had a question about how many computers a supercomputer typically has. You said the biggest one is like 1 million computers all working together. That seems like the biggest example.
Right.
The one you showed us might be the supercomputer at Princeton, maybe? How many
Right.
computers does that
Has on the order of thousands.
Okay, thousands
right?
of computers.
And you know, we often will call them clusters, and supercomputers are just really big clusters. So even if you put two together, that's more powerful than one. And so everything from 2 to 1 million is out there. It exists, and they all serve a valuable purpose.
All right, excellent. And I think you're going to love this question from Ruby. She really wants to know about the actual coding. Like, are you writing code? Talk us through how maybe you meet with a scientist who has a problem they want to investigate. How would you approach the problem, and how would you begin the process of writing software to help solve it?
Right. No, that's a great question. So at a high level, what we do is we have to say, are there things out there that we can reuse that already exist? So maybe there's a library. I'm trying to think of a good example. Maybe if you're trying to take this big block of numbers times this big block of numbers all at the same time. In linear algebra, we call that a matrix multiplication. We can just get a library out there, type in, send these two matrices to the library, and it comes back. Right. In other cases, we have to say, okay, we're going to read in this data file. So if it's the voter registration information, we need to go line by line through the data, bring it in, store it, and then manipulate it, do whatever it is we need to do about it. So I had that one example earlier on of some code that actually does something. It doesn't do a lot. It's actually pretty mundane, but it can give you an idea of how these programs can get to be not just thousands, not just tens of thousands, but hundreds of thousands of lines of code to do a single problem. That's not uncommon.
When you get a new problem, how often is there something already existing that can help you with some aspect of writing the software versus how often do you need to write your own from scratch?
It's a little of both. I've used the car analogy again. If you think about writing a program to solve a problem, it's like building a car. We're not going to go build an engine, build a tire, but we've got to put it all together. So a lot of times we need to take pieces that we can find from all these different parts, stitch them together, and the stitching requires code and glue. And sometimes it's something brand new, and we're going to have to just start from scratch and start writing. But wherever we can reuse it, we try to.
All right, excellent. Well, I know something you're saying is really resonating with the students, because maybe our final question is a direct request to come and visit you on campus and see what you're doing. Do you do field trips?
We have hosted groups before to see the supercomputer and chat about what we do on the supercomputer. So if you'd like to get in contact with me, I'll see what we can do. I don't give the tours. To get a dirty little secret, I don't have access to the supercomputers. They keep it in a locked room in a nondescript building so nobody knows where it is because it's millions of dollars of computing power that they try to keep quiet. But yes, we can do tours and group visits.
Awesome. Well, Ms. Copeland students, thank you for the excellent questions. I want to end with kind of a fun question for you, Ian. You're doing so many interesting things with research software engineering, exploring so many aspects of scientific research, making so much possible. Is there something that is sort of right now being approached through this combination of supercomputers and software engineering that you're excited about, that you're particularly interested and excited about, that this increase in technology and software, maybe we'll get like an answer we haven't been able to get before?
Oh, wow. Oh, now I have to pick one. I think what a few of the things that really interest me, but are neuroscience and computational neuroscience. So how the brain works. We're getting closer and closer to being able to map how the brain actually works. And supercomputers are a crucial part of that. It's a huge problem. It's something that is really pretty staggering when you think about. But watching over the years, the progression, I feel like we're gonna get there, and it's gonna be a really, really amazing discovery when that does happen.
It's very kind of funny to think about our brains trying to figure out computers. They're trying to think about our brains and that relationship of trying to understand, explore both worlds. Very, very cool. Great examples of how research software engineering is really harnessing, as we say, the power of supercomputing. Ian, thank you so much for joining us today. Thank you for sharing these great examples of your work and explaining to us what you do. That is all the time we do have for today. If hearing from Ian has excited your interest in supercomputers and software engineering, I encourage all of our teachers and students to hold on to your seats for our next live stream event. We're going to take it one step further and enter the world of quantum computing. Just when you wrapped your mind around supercomputing and research software engineering, we're going to go another level. Keep looking for new articles on the Reach the World Journey homepage. Again, the link to those articles is in the chat. I look forward to seeing you all in the next live stream event for this program. Until then, thanks again for being here. Keep exploring, and I will see you all next time. Thank you so much, Ian.
My pleasure. Thanks for joining, everyone.